Excellent. Thank you.
All right, very fine. Are we good to go now? We think.
Indeed.
Okay, well, good morning, everyone. And we are going to do a little bit of housekeeping. And then talk more about Flutter analysis. So this is the 7th of April in our new normal, whatever that is. And today we're going to talk about Flutter analysis. And last time we talked about the VG method. You may remember. And we did that for 1 degree of freedom. Now we're going to do it for as many as you like. We're also going to talk about something that's usually called the Pecan Method. And then I'll talk about an exact solution method. So you know that such a method does exist, although it's rarely used, except for students and faculty who want to write a journal article, which we have done.
All right, that helps. Okay, as I was saying before, I was trying to deal with the mute and unmute. Today, we're going to talk about Flutter analysis. And we've done a little bit of that the other day in terms of the VG method, which is the method that is commonly used in industry. And we've done that for 1 degree of freedom system. Today, we want to do it for multi-degree of freedom systems. So it's the same idea, but slightly generalized. There's another alternative that is sometimes used called the Pecan Method, which is considered in some sense better, but more expensive. And then there's an exact solution method, which presumably is the best of all, except it's even more expensive. And that's why people continue to use the VG method, and we'll talk more about that. In terms of coming attractions, on Thursday, we're going to talk about 3D superside flow. That will be Thursday. Then we're going to talk about 3D subside flow. That will be next week. Then I'm going to have a special guest, Danny Levin, who has a lot of experience in using what I'll call industrial strength computational methods and codes. And he's going to come in and talk about Z-Aero, which is a very popular computational tool, computational method, computational code, which allows you to use these kinds of aerodynamics in a Flutter analysis. And if you have access to the Duke computer resources, you can actually use that code. So let me ask you a question. Of all the students out there in cyberspace, do you still have access to the Duke computer system?
Yes.
Okay.
Wait, what do you mean with the computer system, like the software's online?
Well, it's conceivable that if you have a powerful enough PC, you can do this computational on your own PC. But you might need to get to a Duke computer, at least electronically, which will have enough horsepower to do the calculation. That's the question.
Well, in that case, I don't think like any of us students will still have access to that because like we're forbidden to go back to campus.
But you can't get.
We've set up remote access to the Duke computing clusters, so I have access and I can give access to a bunch of the students if they would like to run.
Well, we'll deal with that when we come to it, but think about that. I mean, you can just hear Danny talk about how to do it, but I think you'd get much more out of it if you actually did it yourself. And then you can brag to all of your friends that you've done a real state-of-the-art Flutter analysis. Okay, so Daniel will come in and talk about that. Kai Bastos, who's just finished his degree and as of yesterday is gainfully employed with a CFD firm called Icon, will come in and talk about Buffet, which is a nonlinear flow oscillation, which is very important and which aeroelasticians typically deal with. Then we're going to have some folks come in and talk about hypersonics, and that will be Kevin McHugh, and Maxime Frieden. So that would be hypersonics. And if you've been reading the newspapers before everyone became consumed by the coronavirus, you know that there are many countries around the world trying to be the first, both militarily and commercially, in the hypersonic realm. So it's a hot topic. And then we're going to have a special treat. Michael Lee is going to come and talk about reduced order models, because if you want to go beyond the aerodynamic models that we're using in this course or talking about in this course and use something like the Navier-Stokes equations, using them in their primitive form or in their original form is going to be problematical. And so you need to find a way of reducing the size of the model so that it's manageable computationally. In fact, I just got off the telecon over the last hour, and there are a group of us from several universities that will be proposing something to the Air Force where we're going to take, we hope, something like the Navier-Stokes equations and construct a reduced order model, which will make it usable for aeroelastic purposes. And so Professor Hall, Kenneth Hall, and Jeff Thomas, Professor Thomas and myself hope to be part of that. And then I think the very last talk will be, in fact, by Jeff Thomas. And he's going to talk about yet a different kind of reduced order technique, namely the harmonic balance method. So that's the plan for the next several weeks, and you might keep that in mind. But in the shortest term, hopefully you've read the literature on 3D supersonic and subsonic flow in the book in chapter 4, and you're finding all the typos. Hopefully not too many, but there are some. And then you've also read some of the discussion in chapter 3 about Flutter analysis. And today you have a homework assignment due. So before I proceed to talk more about Flutter analysis, let me ask if you have any questions about that homework assignment. I have not received very many emails in the last several days. I'm hoping that means everyone is proceeding at pace and doing wonderful things with the homework that's due today. Is that true? Hello,
maybe that's true. Might have a logistical question, but this might be for Michael. If we submitted before last class, do we need to resubmit?
So if you have submitted homework 9, I see 9 submissions, which is everyone.
Okay.
Yeah, I've got all submissions for homework 9. You had revisions 8. You were able to resubmit until today.
Okay. Okay. Got it. Okay.
Yeah.
Okay.
But apart from that, I didn't have any questions.
All right, good. Any other questions about that? Hearing none, let's talk about Flutter analysis.
So I do have a question about the guest lectures that you're talking about, the bulleted points you have below. Are these going to be is there like a week dedicated to each lecture, or are some people going to be split, or how will that work?
The plan, subject to change, is that Danny Levin will have at least one class, maybe two. And I've told these folks to allow time for questions. And Kai will have a class. Kevin and Maxime may have a class individually, or they might combine and do one class together. That's yet to be decided. Michael Lee will have a class, and then Jeff Thomas will finish up. So these are basically, and at least I'm not sure, and Michael Lee and I discussed this the other day, I'm not sure when the semester ends. You may recall that we had, 2 weeks of spring break, right?
Yeah.
And so does that mean that we've extended the semester by a week? I had logically, but perhaps incorrectly, assumed that that was true. But I'm waiting for a word from higher authority to say when the semester actually ends.
Okay.
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 But I'm happy to go as long as anyone wants to, but you may have other things. And I think, I understand you may have other courses and other commitments. So we will end whenever the university says the semester is over.
Okay.
Okay? All right. Okay, let's go back to VG Flutter Analysis. And before, we did that for 1 degree of freedom. And now we want to do it for lots of degrees of freedom. So I'm going to start off with an equation of motion, which I hope you remember. There's a generalized mass times a generalized coordinate acceleration plus the natural frequency squared of a certain mode times the generalized coordinate is equal to a generalized force. And we're going to call that equation 1. And just to remind you, the generalized force in our case is due to aerodynamics, and it's the pressure, which we have found out how we can compute at least for 2D supersonic flow, and we'll shortly find out how to compute it for 3D supersonic flow and then 3D subsonic flow. It's that pressure we're going to get from the aerodynamics times the mode shape integrated over the area of, say, the wing. And we're thinking of the deflection of the wing as being the function of 2 spatial coordinates because it's a planar-like structure, and of course time. And it's expressed then as a modal series of these coordinates qn functions of time times psi n functions of x and y. And almost invariably, those mode shapes will be the eigenmodes or the natural modes of the structure. And they were in the real world, as they say, they would be computed from this finite element code. So if you've taken a finite element course at some point, from an aeroelasticity point of view, the utility of finite elements is to find those modes. And once we have those modes, then we say thank you very much to the finite element code and never use it again. So these are the mode shapes. And this is equation 2. Now, from our discussion of aerodynamics up to this point, what I'm about to write down, I think you should be able to readily verify for 2D supersonic flow, but it turns out it's also true for 3D supersonic and subsonic flow. Namely that this Q sub n, which of course depends on time, doesn't depend on space because we integrated over x and y, and therefore the spatial dependence went away, is equal to 1/2 rho infinity u infinity squared. This factor always appears in almost any aerodynamic theory, and certainly in potential flow theory, times a characteristic length squared, which we'll take as the chord, times the span. So if this is a rectangular wing, this is also the area. And sometimes people use the area of the wing, sometimes people use a characteristic chord dimension, a characteristic span dimension, but for our purposes, we'll take it as C times L. And then it's multiplied by some non-dimensional function, like lift, normalized in the way we've chosen to normalize it in our homework assignment, which depends on a non-dimensional time, t u infinity over c, and it also depends on the Mach number. And of course, it depends on all of these wonderful generalized coordinates, because just as we saw, lift in supersonic flow depends on h dot, but it could also depend on the angle of attack, alpha, or the angle of twist. And more generally, for multiple modes, it depends on the modal coordinates. And it depends on all of the modal coordinates, right? Not just one. And maybe I should call this Q sub m rather than Q sub n, because m can be 1, 2, 3, including whatever n is, right? So n varies from 1 up to however many modes we have, let's say 17. And of course, m varies over the same range of integers. Okay? But for simple harmonic motion, that means Q sub n is some Q sub n bar e to the I omega t, or Q sub n bar e to the I, and now I'll normalize both frequency and time. So I have omega c over u infinity times t u infinity over c. And again, as I've emphasized, if I non-dimensionalize time this way, that implies I'm going to non-dimensionalize frequency this way. So with that in mind, I can then write this Qn, this non-dimensional quantity, as it's going to be summed over all of the m, all of the modes from 1 to 17, Q m n, I'll make it a double bar now. Why? Because it's now a function of this reduced frequency k as well as Mach number. Q m bar over c e to the I omega t, and of course I cannot think of that as think of omega and t as being normalized as well. And so this I'll call equation 4. The important point is we're using a linear theory, so this Q sub n is going to be proportional to each of the modal coordinates. That's what a linear theory does for you. And these coefficients that appear here, which will come out of our aerodynamic model, only depend on the reduced frequency, where k by definition is omega c divided by u infinity, and of course the Mach number. Okay? And so for our purposes for Flutter analysis, we just need to realize that we can do this, and out of the computer code that generates aerodynamics, these coefficients Q sub m n are produced. Okay, and in particular, this could be left for a moment if we're looking at H and alpha motion, but more generally, it's something more elaborate, corresponding to more elaborate modes. So now, if we take all of this, if we take from 1, 2, 3, and 4, and we put all this together, and cancel out the common factors ei omega t, we'll have something that looks like 5, which is m sub n minus omega squared because when I differentiate this twice with respect to time, I generate a minus omega squared, plus omega n squared times q sub n bar. All right, that's the amplitude of the q sub n, and then equals, putting all these other things together, 1/2 rho infinity u infinity squared c times L summation over m of q sub m in double bar q sub m bar over c. Okay. Again, n runs from 1 to 17, and so does m. So what we've done by using natural modes of the structure is, on the left-hand side, there's not a summation. So if I write this in terms of matrices, this is going to be a diagonal matrix. But on the other hand, on the right-hand side, where we have the aerodynamics, the aerodynamic forces, aerodynamic pressure in particular, couples all the modes. So these modes are coupled through the aerodynamics, even though we made a great effort by using natural modes for the structure to uncouple the structural terms. But there's a method to our madness. There's an important reason why we want to uncouple the structural terms before we perform the Flutter analysis. So now, what are we going to do? We're going to take equation, we're going to take 5 and divide. We're going to make it non-dimensional. Again, we love non-dimensionalization, as you may have gathered by now. We're going to divide by 1/2, divide by 1/2 rho infinity u infinity squared c, CL, I'm going to divide it by C, okay? And if we do that, we'll get the following. We'll get equation 6, which is now 2 m sub n over rho infinity c squared rho infinity c squared L times minus omega c over u infinity squared. I want to generate a reduced frequency, as you'll see why in a moment, plus omega n c over u infinity squared q sub n bar minus the summation over m q sub m n double bar q sub m bar equals 0. Now, I said a moment ago that I wanted to non-dimensionalize, and that's true, but if you're paying attention, this factor is non-dimensional, these factors are non-dimensional, q sub m n double bar is non-dimensional by construction, but of course I left this in terms of dimension, what are the dimensions of the small q's are. But since it's a linear theory, it doesn't matter. I could divide this by another c and this by another c if I really want to make it non-dimensional. But since it's linear, I don't bother. But what I do now is I define, I'll call it a mass ratio, omega mu sub n, which is this factor 2 m sub n over rho infinity c squared L. What I usually do in Flutter analysis for convenience is I normalize the generalized masses, the m sub n, so that all of these mu sub n have the same value, which I can do because I can choose the normalization of the mode shapes. And typically this is done, and that simplifies the algebra, as you'll see in a moment. And if you do that, then we finally get equation 7, which is almost our working equation for the Flutter analysis. We have a factor mu. Using some shorthand notation, I have minus k squared, oops, because this is a reduced frequency. Then I'm going to rewrite this term in the following way. I'm going to write this as omega n over omega 1 squared. Omega 1 is the natural frequency of the first mode. I could have chosen the ninth mode. I could have chosen any mode I like, but the first mode seems like a reasonable choice. And then this is omega 1c over u infinity squared. Q sub n bar minus summation over m Q sub m n double bar equals 0. Now, why have I done all this? Well, it's because this coefficient, capital Q double bar, only depends on k and the Mach number. So if I choose k, which I'm going to do, then I know this thing from aerodynamic theory. Of course, I know this k. I'm going to choose the mass ratio appropriate to my system. I'll know the natural frequencies of the structure, and therefore I'll know this frequency ratio. And I'm going to treat this quantity as an eigenvalue, because I want to do eigenvalue. I want to go to MATLAB and find the eigenvalues of this system. And to do that, I want to write it in matrix form, of course. So I'm going to take this set of linear algebraic equations for n 1 to 17 and m equal to 1 to 17 and write it in matrix form, treating this as an eigenvalue. Okay? So let me pause momentarily and say, are you still there and still with me?
Yes.
Ah, good answer. Good answer. Okay. All right. So in matrix form, I worked this out ahead of time so I can make sure hopefully you get it right without any typos. In matrix form, we're going to have the following. We're going to have a matrix A, I'll define that in a moment, plus an eigenvalue lambda, I'll define that in a moment, times another matrix B, I'll define that in a moment, times all these Q bars equals 0. And so I'm going to MATLAB or any other software you like. I'll give them the A matrix, I'll give them the B matrix and say, compute lambda for me. What's the A matrix? The A matrix is equal to a diagonal matrix because we used orthogonal structural modes, where each element along the diagonal is equal to mu, this mass ratio, times k squared. And then, because I want to separate out cleanly the eigenvalue, I will not divide this equation further, equation 7 further, by omega n over omega 1 squared. And the B matrix is the I left out a term, so I better go back and make sure I get this right. It's that plus another matrix, or it's actually minus the matrix, minus the Q sub mn matrix, normalized also by the same factor. Okay, so it's two contributions, one from the inertia term in the structural model and the other from the aerodynamic term. And the B matrix is then yes, matrix is just going to be unity then, right? Okay. I'm looking at my equation to make sure I got that right. Yes. Yes. Yeah, yeah, that's fine. Okay. All right. Now, so we define these matrices, and we're going to give these matrices to a bit of software to find eigenvalues. We're going to find the lambdas. Now, remember what the lambdas, I should tell you what the lambdas are. The lambda is defined to be omega 1 c over u infinity squared. Okay, so what do? We specify the Mach number, we specify the reduced frequency, and we specify mu. And of course, we know the ratio of the natural frequencies of the various modes to that of the first mode. So we specify all that and compute lambda. We compute 17 lambdas, in fact. Okay, because there's 17 modes. Now, if you watch closely, and you remember how the aerodynamics come out for 2D supersonic flow, this matrix, this aerodynamic matrix, in general, has elements which are complex numbers. Therefore, lambda will be a complex number with a real part and an imaginary part. Okay? And there'll be a number of them. There'll be lambda 1 up to lambda 17, of course. Okay? But lambda physically has to be a real number. So what are we going to do about that? Well, we're going to do the same thing we did in the 1 degree of freedom case. We're going to generalize our definition of lambda by multiplying it by a factor of 1 plus IG, where we interpret this G as structural damping, a non-dimensional structural damping coefficient. So then we can take each of these values of lambda that we compute, all 17, and for any one of them, what do we have? The real part of one of them is equal to omega 1 c over u infinity squared, okay? And the imaginary part divided by the real part is equal to G. I have a certain airfoil with a certain fundamental natural frequency and a certain chord. By knowing the lambda real part, I have a velocity. And then by knowing the imaginary and the real part together, I know the G. So, but I have this for each of 17 modes. So in general, the velocities will be different for each mode. And of course, the G values will be different for each mode. So what I have to do is repeat this calculation for different values of K, several different values of K, but hopefully not too many, maybe on the order of 10 or so. And then I will be able to plot the value of frequency and also the value of G. Oh, by the way, how do I get the frequency? Remember what K is. K is the flutter frequency C over U infinity, right? Okay. And so from here, I know U infinity in terms of lambda real, and so I can find, and I've specified K, so I now know omega as well, right? So for each K value, I've assumed, for each flow velocity I compute from here, I can also determine the omega that corresponds to that eigenvalue, that each of those 17 eigenvalues, and of course I have the 17 values of G. So then I can construct the famous VG plots. And normally you only construct it for positive values of omega because it should be a mirror image for negative values. And then of course you construct values of G. And you plot omega and G versus U infinity for 17 different modes. And I'm not going to do it for 17 different modes, but the point is the following. If this is the first mode, and let's say 0 is the second mode, I'll just do it for 2 modes, then I'm going to have different values of the 2 modes. The second mode presumably has a higher frequency. But the point is, the numbers I compute to put on this plot, they don't correspond for 2 different modes to the same value infinity. But if I have enough of them, I can see what the curve looks like. And conversely down here, if this is positive G and this is negative G, then I'll have draw them the same way, X, 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 and 0, 0, 0. So I have a curve like this, I have another curve like that, I have a curve like this, I have a curve like this. And what happens is what we saw when we did our simpler Flutter analysis, namely that the 2 frequencies come together and one of the damping values is stable and one of them shows an unstable motion. And remember the interpretation of G. It's the amount of structural damping required to give a neutrally stable solution. So if the amount of structural damping needed to give a neutrally stable solution is negative, and we never have that, we'll never have a neutrally stable solution for this branch, and therefore we interpret that as a stable branch with decaying oscillations. This point is the Flutter point, and I didn't quite draw my here and so forth. And this is a stable portion of this branch, but this is an unstable portion of the branch. And you do this for 17 different routes. Of course, this is all done by a computer. And in fact, in a real Flutter analysis, you might have up to 50 or so modes you would plot. That means keeping track of the modes, particularly since each data point corresponds to a different velocity, is a non-trivial matter. In fact, it is not unknown that people have literally not connected the dots correctly and gotten the wrong answer in terms of the Flutter boundary. So that's a caution to you. So now you understand how this VG analysis is done for as many modes as you like. End of story. Pause. So now questions before I tell you the other 2 ways that sometimes are used to construct a Flutter analysis. Questions? I hear a resounding silence. So this must be crystal clear. Is that true?
Yeah, I mean, I think it's pretty clear.
Okay, yeah. Great. All right, let's go back then and look at what I'll call the PK analysis. So now we're ready to go to PK. It's probably a bad name, but the person who invented this approach called it that, and so we will as well. PK analysis. For this purpose, we're going to go back to equation 7. You remember what equation 7 looked like? This is not written in matrix form. mu times minus k plus this factor times q sub n bar, etc. Right? So let me write that equation down again, and then we'll produce it in matrix form. Okay, this is equation 7. I think I'll just use this equation with, I can write it in matrix form if that helps you, but hopefully I won't have to do that. Here's the idea. Remember, these depend on k. The reason we're doing all these convolutions in terms of how we do Flutter analysis is because we really only want to compute these coefficients for real values of k, because that's much easier than you doing it for complex values. So one thing I could think of doing if I look at this equation is I could think of using an iteration approach. So this is basically an iteration solution. So choose an initial k value. If you're an experienced Flutter engineer, you know that, well, we built an airplane that looked like this pretty much with a little change 10 years ago, and the k value for Flutter turned it out to be 0.3. So guess what? We'll start out with 0.3. Actually, Flutter k's tend to be in the range of probably between 0.1 and 0.5 typically. I mean, sometimes they're lower than that or higher than that, but not often. So we choose an initial k value. That allows us to know what q double bar is. Then we treat k itself as the eigenvalue. So once I fix q double bar for some initial k, then I can treat this as an eigenvalue problem to find that k, right? I can do that. Of course, that k itself is a complex number, right? Because again, this was a complex number, so this is going to be a complex number too, and there are going to be 17 of them. Okay, so what do I do then? So I choose the initial k, then I find k from treating this as an eigenvalue, and there's 17 of these, k1, k2, up to k17. So what do I do then? And they're complex numbers. I take the real part of k, because that's the only part I can use to compute the capital Q double bar. I take the real part of k and put it back in here. And then I compute this k again. Okay? So choose k, choose, oh no, let me put this one. Compute Q double bar for k equals k real as a result of this iteration. And then I just keep looping back. And hopefully this process converges, namely that eventually the k real I get here is almost the same k real I put in here. This method doesn't always converge. That's one thing you should know, but it often does, usually does. The other thing is, note that you have to do this for 17 different modes. You have to do this for all the modes. Normally you don't do it for all the modes because it turns out those 17 modes, there are 2 or 3 that are really important for Flutter and the others are not so important. But you at least have to make sure you get an iteration convergence for the modes that might lead to Flutter. Okay? And then how do you know whether Flutters or not? Well, you look at the imaginary part, because remember, we're assuming a solution form E I omega t, which is E I k times t u infinity over c. So it's the imaginary part of k This is a positive number, of course. The imaginary part of k that determines whether the solution grows or decays with time. Why is this called the PK method rather than the iteration in K method? Well, because the guy who did this originally did not assume a solution of the form e to the I omega t. He assumed the solution of the form e to the pt. E to the pt. All right, but obviously p and I omega have a close relationship. So you'll see the PK method invoked, and people won't even give you the details in the paper. They'll say we use the PK method to find our Flutter solution. Note that this still is not giving you an exact answer, because we're not using all of K to compute the Q double bar. But this does have some advantages. It avoids any discussion of artificial structural damping, for example. And so some people prefer this method. This method turns out to be computationally a little more expensive because it's an iteration approach, but nevertheless, it's still used by a fair number of practitioners. Now, okay, pause. Any questions about that before I give you the exact method?
So far, so good.
So far, so good. All right, let's look at the exact method. This exact method is something that we use in our group occasionally. I'm not sure. There's not many other people have used it, but it's expensive. That's probably why they haven't used it. But it gives you the real answer, and so it gives you a benchmark. So if you were concerned about the answer you're getting back from VG or this iteration scheme, you might try it. In principle, the VG method and the iteration scheme are exact right at the Flutter point, where K, in fact, is a purely real number, right? Where the frequency is purely real and the imaginary part of the frequency is exactly 0. But it doesn't really, those methods don't really tell you what might be happening as you get close to the Flutter condition or slightly beyond it, and you might want to know that. So let's see how that works. Yeah. Let's go again back to equation 8, I think it is, if I can find it. Okay. Here's equation 8, okay? Remember that? When we find the eigenvalues, what we really are doing are finding the values of lambda for which the determinant of these coefficients is 0, right? That's really what you're doing. That's from linear algebra. So now, if we look back at 7, I want to 7. This is before we write it in matrix notation, but let me write equation 7 again and then do a little manipulation. So here's 7. So let me write 7 again. 7 is mu minus k squared plus so forth and so on. That's 7. Now, if I write that in matrix notation, it's just mu, well, I put it all together. It's a diagonal matrix, mu minus k squared plus omega n over omega 1 squared, omega 1 c over u infinity squared minus a Q, just a Q matrix, and all of that times a small q vector equals, of course, the vector 0. So this is just 7 in matrix notation, right? So all I really want to know are the values of K, for example, complex K, for chosen values of all the other parameters. So I could choose view, I could choose omega n over omega 1. I could choose this. And of course, I could choose Mach number. Then I could solve for K, complex K, the real complex K, not the full complex K. And how would I do that? Well, I could define a determinant, which is the determinant coefficients of this entire coefficient matrix, right? That's the determinant coefficients. So I could, for example, choose K values, complex K values, and find D. When I do that, I'll find, by the way, of course, this determinant has to be 0. When I do that, I'll find D has some real part and has some imaginary part. And in general, they will not be 0 because I wasn't lucky in my guess about Q. But I can keep guessing, hoping that someday I will make a guess for K that leads to both dr and di being exactly 0, let's say for some value of flow velocity. But you need a little more systematic way of doing that, and here's the way you do it. I'm going to plot versus the real part of K, both the real part and the imaginary part of D. And the real part of D goes something like this. So for example, here's the real part of D. And that happens to be the real part of D when Ki is identically 0. Okay? And here's some other real part of D for some imaginary part that's greater than 0. And here's another real part of D for some Ki that's less than 0. Remember, in our notation, if Ki is less than 0, and we make both dr and di equal 0, we found a Flutter solution. But then, I'm also going to plot the imaginary part. And the imaginary part, I'm going to use a red pencil, which I hope you can see. So here's the imaginary part. Okay, also for Ki equal to 0. And here's the imaginary part for a Ki greater than 0. And I'm going to extend this back a little bit. Here's the imaginary part for Ki less than 0. So when the imaginary and real parts cross, that means they're equal, right? And those are very special points. So I'm going to highlight those with a red dot. So what I really want is dr and di not only to be equal, but I want it to be 0. So I'm going to interpolate along that curve, and it looks like the flutter point is about there. which gives me a value of KR and KI if I have a finite grid in terms of different values of the real and imaginary part of K and the corresponding real and imaginary parts of D. This is very expensive because I had to evaluate my aerodynamic forces many more times than in the other methods, and I have to evaluate the aerodynamic forces for complex values of K, not just real values. Now, the good news there is the basic theory we've developed, although we didn't emphasize this at the time, when I assume EI omega T and find the solution for the aerodynamics, that omega can be a complex number. It doesn't have to be a real number. It's just that most of the computer codes that are written and used in the industry assume that omega and K are real numbers. But anyway, this gives you an exact solution, and that's a good thing. So I see, I should probably exact solution. Okay, so if you ever want an exact solution, there's a way to do it. Probably your boss at Airbus will tell you that he doesn't have time to wait for you to get an exact solution. But on the other hand, if the solution you're getting out of these other methods looks questionable, then you and your boss might decide that using this method wouldn't be an entirely bad idea. So you are now privy to the three ways of Flutter analysis that you're likely to encounter. And on Thursday, we're going to do 3D supersonic flow, which means that we will be able to compute, there it is, Q double bar for 3D supersonic flow, okay? And then we'll do subsonic flow. I think that's all I'm going to tell you today, unless there's some questions. Any questions? I don't hear a single question. And that means that how many typos have you found so far? Anyone want to offer a number?
17.
Really?
Nah, that's just your
no, no,
that's just your favorite number, so I just threw that out.
How many? I'm sorry, I still didn't hear you.
I found 9.
9. Oh, that's a goodly number. Anyone found more than 9? Now, were you really picky when you called it a typo, or were those really?
I did not count my the spelling ones that I found last week.
Okay. All right. All right. Well, if you have not yet found the typos for Thursday, do that, and I'll look forward to getting to that, and I'll look forward to seeing what you produced by way of lift results in the homework due today. Did you compare your answers for today? Did you compare those to that graph in the book, and did you get the same result?
Yep. Yep.
Sure did. That's a good thing. That's a very good thing. All right. Very good. Well, that's all I have to say for today, unless there are questions or comments. Any before we close for the day?
The typo homework that got pushed back to next Tuesday, correct?
Oh, did we move it to Tuesday? Okay, I'm easy. We can do that on Tuesday. Of course, that doesn't prevent me from assigning another homework on Thursday, right?
Maybe not.
Okay, actually, I don't plan to assign one, but you'll have a fairly heavy assignment from Danny. So I'm going to cover over the next lecture or two. In fact, we might, well, I don't think I can do subsonic and supersonic flow in one lecture, but maybe over the next 2 lectures, I'll give you the basics of what's in those computer codes. And then when Danny talks to you, you'll have a chance to exercise one of those codes and see how it works in practice. Okay, well, good to be with you, and be safe out there, and I'll see you on Thursday. I'll at least hear you on Thursday.
Thank you, Professor.